Hello everyone and welcome to the York Festival of Ideas. My name is Josie, I'm an astrophysicist and lecturer in the School of Physics, Engineering, Technology here at the University of York, and I'll be chairing the event today. So it's my great pleasure to welcome you all. So it's my great pleasure to introduce our speaker today, Louise Devoy. Louise is Senior Curator at the Royal Observatory Greenwich. She has a background in astrophysics and the history of science and has worked at various museums in the UK and abroad. Her research interests encompass astronomical instruments, women in astronomy, and networks of knowledge exchange between historic observatories. In Louise's most recent book, Royal Observatory Greenwich, A History in Objects, she uncovers the development of Britain's first state-funded scientific institution, from its founding by royal warrant in 1675 to the present day. So I'm very much looking forward to hearing more from Louise.
Thank you, Josie. So last year, 2025, was our 350th anniversary. So that means it's a great opportunity for us just to stop and reflect on 350 years of inspirational science, amazing technology, and pioneering people. People such as astronomers, clockmakers, technicians, instrument makers, and even lady computers, who all contributed to the observatory's work. The work that now means that we can tell what time it is and where it is anywhere on the planet. So just before we start, just a quick look at the site as it appears today. Has anyone been to the Royal Observatory Greenwich? A couple of hands? Yep, most people. Excellent. So you'll be familiar with this. This is the facade as seen from the north looking south. You've got the classic Christopher Wren brick building.
Is it possible to dim the light so we can see the pictures better?
Good point.
No, I'm afraid we can't.
I'm afraid not, but thank you for asking. Thank you. So we've got this wonderful, beautiful facade, and then you can see just on the left-hand side the onion dome that houses the Great Equatorial Telescope, the largest telescope of its type in the UK. So it's quite a sprawling site. It's situated within Greenwich Park, about 5 miles east of central London, and it really is a privilege to work at such a beautiful and historic location. So today I'm going to give you an overview of my book that was published to celebrate the anniversary last year, The Royal Observatory Greenwich, A History in Objects, and this book covers about 100 objects that I chose from our collection, which was quite a task. We have about 2,000 astronomical instruments and about another 2,000 clocks as well. So it was quite tricky trying to pin it down. But I wanted to really show and sort of emphasize how diverse the observatory was. So you'll have all the classic clocks and telescopes that you'll expect, but also paintings, photographs, postcards, and even a few items of clothing that were worn by the astronomers as well. So a very rich and wonderful history that I've tried to convey through these stories. Now, before we start, there are a couple of concepts that I think would be really helpful just to refresh ourselves. So starting off with latitude, if we go back to the times of the ancient Greeks, about 2,000 years ago, people such as Ptolemy, who created this sort of grid system or coordinate system as a way of working out where we are on this planet. So latitude gives us a measure of our north-south position. How far away are we from the equator, this line or this belt that encircles the Earth here? Now for navigators, they could measure this fairly easily. During the day, they could use this instrument called a cross staff. So you want to measure the height of the sun above the horizon. And the idea is that you slide the vane, that middle section, up and down the rod until you fill the gap between the horizon and the sun, or the object that you're measuring, and then read off the numbers on the scale, on the rods. And then likewise, you can repeat this at night, but this time using the pole star, Polaris, whose height above the horizon gives you your latitude. So this is fairly straightforward. Longitude, or your east-west position, this is a bit more tricky. So we can use these imaginary lines called meridians that run from pole to pole. We imagine them all the way round. Now today we're quite familiar with thinking of the prime meridian running through Greenwich. But for the ancient Greeks, they actually chose their prime meridian to go through the Canary Islands because that was the furthest west that they were aware of. So that made sense as their starting point. But over the centuries, we've had quite a few different meridians. And later on, I'll explain why Greenwich is so significant and why that was chosen as 0-degree longitude for everyone. And then the third concept that's really helpful for the story is thinking about longitude and the Earth's rotation. I promise this is the only bit of maths tonight. So we have to remember that the Earth rotates on its axis once every day, so that's 360 degrees. So if we divide that by 24, we can tell that the Earth is rotating 15 degrees per hour. So if we know the time difference between two observers at the same time, we can work out their longitude difference. So for example, a 3-hour time difference is equivalent to 15 times 3 or 45 degrees longitude difference. Now, simple in theory, but fiendishly difficult in practice to measure, especially out at sea. Now, of course, for the astronomers, the answer lay in the skies. How can we measure longitude using astronomy? So we want to find a way of comparing what two observers are seeing at exactly the same time. So what about lunar eclipses? When the moon passes into the Earth's shadow, turns a very distinctive blood red. Well, you could use this, but you'd have to wait a long time. It might take several months before successive events. So it's not frequent enough. Then later on, from 1610, we had the option of using Jupiter's moons. Thanks to Galileo and his work using telescopes, he was able to detect these 4 bright dots of light, the 4 moons, that orbit around Jupiter over several days. And you can use different configurations of those moons to work out comparisons. But as you can imagine, trying to observe through a telescope on a rocking ship, trying to precisely measure where those 4 dots of light are, virtually impossible. So the next best option was to use the moon. It's big, it's bright, it's easy to find in the sky, and we can measure its position against the background stars to work out this calculation. Now, this is the easiest to observe, but it's also the most complicated. The moon's orbit is quite variable. It's really quite difficult to predict where it's going to be, so it still needed a lot of work before this would become a viable technique. So really, for astronomy to become the way of measuring longitude, we need better instruments for measuring those key angles in the sky. We need better predictions. Where is the moon going to be against the background stars? And because of the moon's erratic orbit, we need better maths so we can make those predictions more accurately. So a lot of work still ahead. Now, other people thought, well, why don't we take a clock instead? Imagine you have a timekeeper set to a known time, say the time at your home port. You head out to sea, you're in the middle of the ocean, you can measure your local time from the sun or stars, and then you can look at your clock, see what time it is back home, and use that to compare and to figure out your longitude. Well, in theory, yes, but you need a really reliable clock that runs at a constant rate, and there are quite a few factors that make this very difficult. First of all, again, you're on a moving ship. Some of the most accurate clocks by the 1650s were pendulum-based. Can you imagine trying to use a pendulum clock on a rolling ship? Virtually impossible. You need to be able to work across a range of temperatures, because you might be travelling, say, from London to the Caribbean, maybe up to northern Canada, North America, back to the Scandinavia, back down to London. Your clock is going to speed up or slow down with all the temperature changes. So that's not going to help. And also you need a timekeeper that doesn't require a huge amount of maintenance. And clocks and watches in this period were quite unreliable. They stopped, they got stuck. So yeah, still lots of challenges ahead. So these ideas started to bubble along, and eventually it wasn't just astronomers and clockmakers who were interested in longitude. Governments and kings started to take an interest as well, because by now, by the 1650s, new trade routes were opening up between Europe, Africa, Asia, and the Americas, and trying to figure out your longitude at sea wasn't just a practical problem, it also meant you could get quicker trade routes, make more profits, and pay more taxes. So there was a lot of interest, a lot at stake in trying to get more longitude. Now, things really started to kick off in 1667 with the construction of Paris Observatory. And then in the autumn of 1674, a French astronomer came to the English court claiming that he and his colleagues had created a much better and improved way of measuring longitude. Now, this didn't please the king, Charles II. He asked members of the Royal Society to look into this, and they recommended that Britain should have its own observatory as well. This led to the appointment of John Flamsteed as the new astronomical observator, later the Astronomer Royal, in March 1675. And then a few months later, Christopher Wren, who also was an astronomer as well, he was then appointed as the architect of this new state-funded national observatory. So Flamsteed set to work about a year later, once the structure was complete, and he had two main tasks. The first one was to create what we now call Greenwich Mean Time. If you measure the sun as it crosses the meridian, that north-south line, you'll notice that there isn't exactly 24 hours between each crossing. It might vary by about plus or minus 15 minutes from day to day. Now, for most people at the time working on the fields, in agriculture, that didn't matter. They just needed to know how many hours of daylight there were. But for astronomers, this was a big problem. They needed something more accurate. So they decided to create an average or mean day of exactly 24 hours all day, every day, all through the year that was much easier to keep track of with a clock or a watch. And that gave birth to Greenwich Mean Time that we're so familiar with now. The other challenge for Flamsteed was to prove that the Earth rotates at a constant rate. If you remember thinking about longitude, time difference, we're assuming that the Earth rotates at a constant rate on that 360-degree turn. So Flamsteed used the stars and these very accurate clocks installed behind the walls of the octagon room in the new observatory to time that rotation period, and he did indeed prove it right, for now at least. And then a couple of hundred years later, we actually discovered these very slight variations in the Earth's rotation, but we'll come to that later. So after 4 decades of very diligently watching, observing, recording the stars, Flamsteed passed away in December 1719, leaving behind his work, and it was up to his wife Margaret and 2 of the assistants who really pulled it all together and published this fantastic, very accurate star catalogue of about 3,000 stars. And then a few years later, in 1729, they published a pictorial version as well, very beautiful sort of illustrated atlas. Now, did it solve the longitude problem? Well, sadly not. Unfortunately, it was aimed at the wrong audience. Flamsteed had written it for other astronomers. It was way too complicated for Joe Blogg's Navigator out at sea. It was too academic. It was written in Latin rather than, say, English. It was too complicated. You needed really good maths to understand it or to use it. It was very bulky. I've seen the volumes in our library. They're about this big, so not exactly pocket-sized. And it was just way too expensive. So a fantastic start, a really good piece of scientific work, but this still isn't going to help your poor old navigator out at sea to calculate his longitude. Now, thankfully, Flamsteed wasn't the only one interested in solving longitude. Other scholars and businessmen really sort of championing the government to do something. They were getting fed up. They'd been waiting for Flamsteed for years, since 1675, and they still hadn't really solved the longitude problem. So in 1714, the British government passed the Act of Longitude, offering a series of financial rewards for anyone who could come up with these ideas to solve longitude at sea. And this was really crucial because people were investing a lot of money in setting up plantations in the Caribbean. And so for them, longitude really would help improve their profits. The maximum prize was £20,000, equivalent to millions today for someone who could come up with a suitable answer. Now, as you can imagine, with any sort of prize, there are lots of weird and wonderful and wacky ideas that were proposed. But eventually, one of the ideas that really started to take shape was to create some sort of clock or timekeeper that you could take to sea. And this is where we start to see the work of John Harrison, originally from Yorkshire, yay, but he grew up in Lincolnshire, and he was a carpenter who became really interested in clocks. And in the 1720s, he came down to Greenwich. He met with Edmund Halley, who is now the 2nd Astronomer Royal. He said to Halley, I've got an idea, what do you think? Halley wasn't too sure. He wasn't a clocky himself, but he knew a man who was. This was George Graham, who was the successor to Thomas Tompion, the man who'd made those pioneering clocks at the very origins of the observatory. Graham and Harrison reputedly talked for 10 hours, and then eventually Graham decided to invest in Harrison's ideas. So Harrison went away and started working on what became known as H1, his first timekeeper. Now, he had to address three main challenges. First of all, motion. So instead of using a pendulum, he created this spring bar balance system instead, so much more stable on a moving ship. For temperature variation, he added in a series of very thin rods of brass and steel that expanded and contracted at complementary rates and effectively cancelled out any variation from temperature change. And then for friction, Harrison ingeniously went back to his carpentry roots and remembered that there's a natural hardwood called lignum vitae that secretes its own natural oils. So the clock essentially sort of lubricates itself. Even to this day, we don't have to oil this clock. It still runs itself, and we just wind it every morning. So some really interesting, innovative, and pioneering ideas. He created this timekeeper. It was trialled on a voyage to Lisbon and back. It performed well, but not quite well enough to get the full reward, but he did get some money from the Board of Longitude, the people who were overseeing the active longitudes, and he developed his ideas further. So this then carried on with what we call H2, seen here on the left. Again, similar principles. The key innovation here is a remontoire, which is a spring that keeps the power running through the system more consistently. But after 2 years on H2, he'd had enough, decided to start again, this time with H3. Now, instead of the spring bar balance, you've now got a circular wheel balance instead. You've got a remontoire for that energy. You've got caged roller bearings to reduce friction, which look a bit like sort of those fidget spinners that were all the rage a few years ago. And then he's converted those bars of brass and steel into a bimetallic strip. And this strip is still the key principle behind your kettle and your toaster today to switch off at certain temperatures. So lots of ideas, but it really took him another 20 years to really work on it. Then in the 1750s, Harrison had a complete change of mind and realised that actually, rather than creating these big, bulky timekeepers that weigh about 40 kilos, why not go for a rather sort of oversized pocket watch instead? Now, this completely flew in the face of conventional wisdom at the time that said that watches weren't accurate enough for this sort of work. But he realised that he could take concepts from his previous prototypes, put them all together, and you end up with this H4 design that beats very rapidly, about 5 times a second. It has extra gold for extra balance, weight, and stability, and he included miniature versions of those remontoire and bimetallic strip. Now, it was trialled at sea because that was part of the condition of the financial reward, and it performed exceptionally well, well within the requirements. You would have thought he'd be home and dry. Nice way to end with a sort of millions in the bank, effectively. But unfortunately, it took many years and even intervention from the king, George III, before Harrison finally received a full chunk of the reward just a few years before his death. Now, he claims that he didn't get the full amount. Some historians have added up all the amounts of money that he was awarded by the Board of Longitude over his lifetime. And if you do that, you come out with a figure of around £23,000. But supporters of Harrison would argue that a lot of those payments were actually development costs or expenses. So the jury is still out as to whether he's got the full reward or not. Now, H4 was very expensive, very complicated, and it was pretty much a one-off. It took about 2 years to make. This still was completely out of reach for your average navigator at sea. It took other watch and clock makers from France, Switzerland, and here in England, most notably John Arnold and this gentleman, Thomas Earnshaw, to take Harrison's ideas and make it into something that could be effectively mass-produced. Earnshaw's sort of great insight was to realise that it could be made in different parts. So the clock, or the chronometer as it became known, might start off being made in Lancashire, then it would be sent to Birmingham, have some extra parts added, and then sent to London for finishing and assembly before being used. And this really brought the costs down as well. So now these very accurate sea clocks, known as chronometers, started to be used from around 1780 onwards. So while the clockmakers were busy working on these chronometers, what were the astronomers doing? Well, back at Greenwich, the astronomers were busy doing measurements. So you have telescopes like this. You're set up looking due south. You're aligned on a meridian, that north-south line. You open up the roof hatch, and you're waiting for the stars to cross as they move from east to west. And as each star crosses the meridian, you're listening for the beat of the clock. Tick, tick, tick. And you're estimating to the nearest tenth of a second. Have a go at home, see if you can do this, to try and accurately map the stars and to make the best star charts available. This was known as the eye-ear method, but as you can imagine, it was quite tricky. So to help him, the Astronomer Royal recruited some teenagers with very sharp senses, but as you can imagine, it was very dull, repetitive and tedious work. You're sat under the telescope, it's freezing cold, and understandably, the assistants only tended to stay for about 3 to 6 months. Now, when I was doing the research for my book about these stories, I found quite a few accessories, and I have to admit that these are some of my favourite objects in the book. Starting off with this wonderful observing suit made of wool, silk and linen, made for the Astronomer Royal in the 1760s. And we know he actually wore it because it's quite well worn, especially on the rump. And it has lots of scuffs, it's got a few worn patches, but it would have kept him nice and toasty. I like the fact that the leggings go right over the feet, so there are no gaps, no drafts around your ankles. But I'm curious to know what he wore on his head. Was it some sort of hat, some sort of wee willy winky type hat or something? Intriguing. Then in the middle, we have this very bespoke alarm clock where you have the numbers around the edge, but you also have the names of the stars: Aldebaran, Sirius, Castor, Pollux, Betelgeuse. And the idea is that every time this star crosses the meridian, you get a little ping, just like a sort of notification to say it's crossing. And then if you want to observe a specific star, you insert a little brass peg into the hole next to the name of the star, and then 5 minutes before the star crosses the meridian, you get a very loud alarm ring to get you up. So you have to get dressed, go down to the telescope and get ready to observe. So a really bespoke but very useful piece. And then finally, on the right-hand side, we have a very simple but really important instrument. This is a fork that was used for catching spiders. And the idea is that you get the spider onto the fork prongs, you stand on a chair or a table, don't try this at home please, and you let the spider drop between the prongs and you keep rotating it, and eventually you get a series of threads between the two prongs. You leave them dry out and then you extract them, and you can use these threads as vertical reference lines in your eyepiece because you want to be able to time and count down exactly when that star crosses the meridian. Now, astronomers tried various materials: cotton, silk, metal, even human hair, but they found that spider silk was the best because it didn't sag or stretch too much depending on the humidity or the temperature change. So this was a really sort of useful material, and they continued to do this right up until the 20th century. So by the 1760s, the astronomical method for measuring longitude is really starting to take shape. So we now have this book of data from Greenwich, the nautical almanac, that gives you the position of the moon every day, every 3 hours for the year ahead. So when you're out at sea, you can measure the moon and then look at the book and see what time you'd see the same angle at Greenwich. You've also got better angle measuring instruments, most famously the sextant, so you can now measure that crucial angle between the moon and a bright star. And you've got better training as well. You've now got these cheat sheets where you literally do all the measurements and fill in all the numbers, do a bit of maths, and your latitude and longitude pop out of the bottom. Now, previously, it would have taken about 4 hours to do all the angle measurements and to do all the maths to work out where you are, by which time your ship has obviously moved. But now with these materials, with these instruments and this calculation sheet, you can now work out your longitude within 30 minutes of work. So a real sort of change of gear in making that possible. So longitude, finally, we've got a solution. The observatory is earning its keep, but the astronomers are not just working on longitude, they're doing other projects as well. So throughout the book, I'm going to try and mention expeditions that were useful as well. Most famously, the transits of Venus in 1761, 1769, and then later in 1874 and 1882. These are very rare alignments between the Sun, Earth and Venus that occur in pairs, roughly once a century. And what you see is this little black dot of Venus moving in front of the Sun for about 6 hours. And if you have lots of observers positioned all around the Earth, taking these measurements, you can then use the geometry of all their observations to work out the distance between the Sun and the Earth. This is what we call our astronomical units, and from that you can work out the scale of the solar system. So a really important exercise, and people travelled all around the world to get the best observations. Then moving forward into the 20th century, in 1919, we had another total solar eclipse, and this provided a great opportunity to test Einstein's theory that gravitational masses such as the Sun can bend light. So if you take a photograph of the sky where the eclipse is due to happen before, during and after the eclipse, you can measure how much the stars have moved in position. It's absolutely tiny, tiny fractions. But if you can measure that, then you can work out the deflection from gravitational theory. Greenwich astronomers were very much involved with this, and it was their work that proved Einstein right. So a really significant milestone in astronomical history. Now, I also wanted to show how the observatory expanded its remit, particularly in the 1800s. It wasn't just astronomy for navigation and timekeeping. In the 1830s and 1840s, we started to take measurements of the Earth's magnetic field. Polar explorers had noticed that as they went further towards the poles, their instruments, especially their compasses, started to behave a bit erratically. What's going on? So around the world, various observatories started to collect daily magnetic measurements to try and help scientists understand the nature of the Earth's magnetic field. So we have instruments such as this galvanometer on the left, where you have a suspended needle that twitches in responses to fluctuations in magnetism. Then in the middle, we have this galvanometer, where you effectively plug it into electric cables running through the Earth to measure electric currents that vary throughout the Earth. And then this was also the age of meteorology. People started to collect regular weather data, so temperature, pressure, and this gadget was used to measure sunshine, where you have a piece of card laid underneath the glass sphere, and then as the sun moves through the sky, it causes a scorch or a burn mark to appear in the paper underneath the lens, so you can measure how long the sun has been out for that particular day. Now, all of these measurements took place in a special structure known as the magnet house. This building was composed entirely of wood because they didn't want to have any metal that might interfere with the instruments. And then the poor assistants had to climb up the ladder onto the roof to take all the meteorological measurements as well. So quite an involved task. Now, alongside this, the observatory was busy sending out time as well, because by the 1800s, Greenwich Mean Time wasn't just for astronomers and navigators. It was starting to become part of our everyday life. So starting in 1833, a time ball was installed on the northwest turret, and the idea is that the ball drops at precisely 1 p.m. every day, so that mariners waiting down on their boats down on the River Thames could look up at the observatory, see the time ball drop, and then check their chronometers to see if their chronometers are running a bit too fast or a bit too slow, and then you can factor that into your longitude calculations. Now, that's fine if you're physically in Greenwich itself, but what if you're somewhere else? How are you going to know what time it is at Greenwich? Well, thankfully, in the 1850s, we had cable technology. So now the observatory used to send out telegraph signals twice a day. These telegraph networks ran alongside the railways. And it was the railways who really made Greenwich Mean Time part of our daily lives. Up until 1847, railway timetables were set according to the local time at the main terminus. So, for example, if you got a train in Manchester, the timetable would show local Manchester times. But imagine if you're down in London, you've got to get a connecting train, say, to Norwich or down to Cornwall. How are you going to convert between all those time differences when there's about a 30-minute time difference across the whole country from east to west? So instead, all the railway companies decided to adopt Greenwich Mean Time, and that's very much why we still use Greenwich Mean Time in our everyday lives now. Then in the 1920s, we went one step further with the broadcast of GMT via radio signals, most famously the BBC 6 Pips. Does anyone listen to the 6 Pips today? Yep, my dad still checks his watch according to the 6 pips. Yep, it's very much part of our British culture. So Greenwich Mean Time really is important for everyone. Then at the same time, we've also got changes in astronomy itself. In the 1850s and the 1860s, chemists working in laboratories realised that they could split light from a burning sample using prisms, which would then give them a pattern or a series of lines that they could then use to identify the nature of the chemicals. Now, astronomers thought, we've got lots of burning sources in the sky. Why don't we use spectroscopy to do the same, to tell us about the chemistry of the universe? So they started to adopt spectroscopy for use on telescopes. So we end up with these spectroscopes that you can slot onto a telescope. So now when you look through at a star, you can see its spectral pattern and see what chemicals are in the star. You can also tell if the star is moving away from us, if the lines are shifted towards the red end of the spectrum, or if the object is moving towards us, the lines are shifted towards the blue end of the spectrum. So much rich information by using this technique to analyse starlight. And spectroscopy is still a huge part of contemporary astronomy and astrophysics today. Now, by the 1880s, there were quite a few national observatories all around the world, each defining their own prime meridian. So, for example, if you bought a map in France, 0 degrees longitude would go through Paris Observatory. But if you bought a map in Brazil, 0 degrees would go through Rio de Janeiro instead. Now, as you can imagine, this became super confusing if you're trying to do international travel, trade, and communications. This is the age of steamships, railways, telegraph networks, submarine cables going around the planet. People needed to coordinate. So in October 1884, there was a conference held in Washington, D.C., where people got together and tried to decide on having just one prime meridian of the world that everyone could use. Now, there were 4 main contenders: Greenwich, Paris, Berlin, and the US Naval Observatory in Washington, D.C. These were the 4 observatories that had the best instruments at the time. Paris Observatory was about to move, so that was disqualified because there's no point setting up a meridian if you're then going to move your telescope. And then eventually it came down to a matter of convenience, because by this stage the majority of shipping companies, about 70%, were already using British maps, charts, and also the Nautical Almanac, all based on the Greenwich Meridian. So it was the most pragmatic decision to choose the meridian that most people were using anyway, and that's why Greenwich became 0 degrees longitude for the whole world. Now, this really was the age of the major scientific conference, because then just a few years later there was another conference, this time at Paris Observatory, and about 20 observatories got together and decided to create a photographic atlas of the entire celestial sphere. They'd realised that with photography, you could create an atlas that shows much fainter and further stars than just by visual observation alone. So they divvied it all up between them. You do this part, I'll do this part. Fine, let's get it done, say, 5 years' time. But, a bit like HS2 and all great projects, they realised that they'd bitten off more than they could chew. It was a really involved project. And they thought, hang on a minute, we need more people. But we also need to keep the costs down. I know, why don't we employ women instead? So this is when we start to see women employed at Greenwich as professional astronomers for the first time. Even though they were effectively Cambridge graduates, they'd all studied the mathematical tripos, they were paid the same as the teenage boys who just left school. But they were undeterred, they worked incredibly hard for the next few years. They took photographs, they worked several nights a week, taking these very detailed photographs of the stars, and then during the daytime they plotted and measured the stars using these machines, these plate micrometers, to give us the most accurate results. Now, it wasn't just all about the stars. By 1892, the sun had started to become more active as part of its 11-year cycle, and the consequence of this was that there were more sunspots. And the poor assistant, Walter Maunder, was really struggling to cope with trying to record all of these sunspots, trying to photograph them every day. And so some of the women, in particular Annie Scottdill Russell, was assigned to work on these photographs every day. Annie and Walter worked together for the next 2 or 3 years, and they got on really well. In fact, so well that they decided to get married. But there was a slight hitch in that at that time, married women were not permitted to work within the civil service. So poor Annie had to resign, but I'm very pleased to say that she managed to continue to work as a volunteer astronomer, and in particular, she became famous for her work as an eclipse photographer. She went on expeditions, and she managed to design cameras that could capture very wide-angle shots of the sun and to detect these streamers in space. Really remarkable work. Then in 1904, Walter and Annie sat down one night and realised that they could plot the number of sunspots that had been tracked at Greenwich since the 1870s. And in so doing, they created this very unique and distinctive pattern known as the butterfly diagram. And this really is about trying to understand the nature of the sun and its activity. And this diagram still underpins modern solar studies today. Now, Annie and Walter were really passionate about astronomy, so much so that they used to write books. They were very famous popularisers. One of the most famous books is called The Heavens and Their Story. If you ever get to see or find a version in a second-hand bookstore, I'd strongly recommend having a look. It's beautifully illustrated, and it's written in a very engaging way. Now, Annie and Walter weren't the first Greenwich astronomers to popularise their work. A few decades before, Edwin Duncan had written The Midnight Sky, very much a how-to guide on how to observe the stars from different locations. And then later on in 1907, there was a novel, The Secret Agent. Did anyone see the BBC adaptation a few years ago about the secret agents? Have a look at if you can at some point. This is based on a real life story. So in the 1890s, I think 1894, there was a bomb attack that occurred just outside the Royal Observatory. The bomb was triggered by a French anarchist, Marshal Bourdin, and there's still speculation today about whether the observatory was his intended target or not, or whether he just simply tripped and detonated his acid-filled bomb too early. But it went off, caused alarm. Bourdin died a couple of hours later from his injuries. But it sparked a lot of interest, and Joseph Conrad used it as the inspiration for his novel, The Secret Agent, that came out later. By 1900, the site is starting to get quite crowded. We've got new buildings, new telescopes. They're looking now for more observations of the moon. We're constantly trying to refine our understanding of the moon's orbit for better predictions. We're also looking for comets and asteroids. And in particular, we had the return of Halley's Comet in 1910, and Greenwich astronomers were very much involved in trying to predict when it would first be visible. And this really is the sort of the golden age of astrophotography. People are really starting to use these bigger telescopes to collect more light and to see further. So now you might have telescopes that, rather than being fixed on a meridian, your telescope is now tracking an object for about 3 hours to get photographs of things previously unseen. Now, it wasn't just all work and no play. I'm very pleased to say that the Greenwich astronomers were quite a sociable bunch as well. So, for example, we had the hockey club where people got together. There was football, there was cricket, and there was also a camera club because photography was a really popular hobby as well. It wasn't just something for the astronomers to do during their jobs. They actually went on trains, went down to the coast, went out into the countryside and took their own photos, and then they had an exhibition once a year to showcase their work. And this reminds me of our Astronomy Photographer of the Year competition that we still hold now, and we display every year at the National Maritime Museum. Now, by 1914, we're entering the First World War. The war broke out in August of that year. Some astronomers were actually away on eclipse expedition out in Siberia. They had to rush back to England, leaving their instruments behind. And I'm pleased to say that the instruments were safely stored at St. Petersburg Observatory, and they were retrieved after the war. So they came back. And this is where we now start to see a shift in that the observatory's work is much more focused towards military objectives. So now the priority is to test loads and loads and loads of chronometers for the Admiralty that they can then use on ships as part of defence. So we have all of these chronometers in the observatory. They were checked every day against the accurate clocks set by the stars. And in the lower picture, you can actually see the gas ovens where they used to put the chronometers in there and bake them, say about 40 degrees, to see how well they cope with tropical temperatures. There was also a top secret binocular testing program because the guys out in the trenches were running short of binoculars. So there was a public appeal, lots of instruments were donated, but they weren't necessarily in good shape. And so the astronomers would disassemble the binoculars, clean them, check the collimation using telescopes, and then put them back together again. And overall, we tested about 3,000 pairs of binoculars during the course of the First World War. Now, in the afterwar period, the observatory is starting to come sort of almost under attack from its surroundings. You've got more houses, industrial units growing up around the observatory, making it very smoky, dirty. You've also got electric railways crisscrossing the park, making it impossible to make those very sensitive and delicate magnetic measurements. So the magnetic observatory had to move out to Abinger in the 1920s. You can see some of the quirky instruments here. And even the telescopes were starting to suffer because they were getting grit and soot on the telescopes, on the mirrors, on the lenses, and it was just becoming really difficult to observe. Now, the Astronomer Royal in the 1930s, Harold Spencer-Jones, started to make some inquiries about moving the site away from Greenwich, but his plans were suspended because of the Second World War. At the same time, astronomy and also horology was undergoing a major shift. In the 1920s, we had a new type of accurate pendulum clock known as the short free pendulum. This is where you now have a pendulum clock suspended within a tank, a vacuum, so that it's less disturbed by air resistance and so on. And this clock was so accurate that they now started to detect very tiny variations in the Earth's rotation. It wasn't quite as constant as we previously assumed. This had implications because the Earth was our fundamental timekeeper, but now it's not so reliable as we thought. People started to experiment with new technologies. In the aftermath of the First World War, radio technology and quartz technology really came on apace, and we started to have the emergence of quartz clocks. So now, instead of a swinging pendulum, you've got an oscillating or vibrating quartz crystal that you can use as your timekeeper. And then this was mirrored after the Second World War with the emergence of the atomic clock, now where you're using microwaves, partly developed from radar technology, now being used to excite cesium atoms, and they're being used as your timekeeping standard instead. So a huge shift away from using astronomy as your timekeeping standard to now using laboratory equipment. And this is still pretty much what we use today. So finally, in the afterwar period, 1948, the observatory did indeed move. It went to Herstmonceux down in Sussex. It's an incredible site that's still open to the public. I'd highly recommend a visit if you get the chance. And you can still see some of the telescopes that were originally at Greenwich and that were later transferred down there. But unfortunately, the writing was on the wall for this site as well. This closed in 1990 because by this stage, it was actually cheaper and easier to build telescopes elsewhere, say the Canary Islands, Chile or Hawaii, cheaper and easier to get better observing conditions there and then just fly out to British astronomers rather than building new telescopes here in the UK. So what happened at Greenwich? We became a museum, so the site gradually started to open to the public in a limited way in the 1950s, then in 1967, and since then we've grown and grown. Our main attraction is, of course, the historic Prime Meridian, 0 degrees longitude, where you can stand with 1 foot in the west and 1 foot in the east, and we welcome around 700,000 visitors a year. We are open for now, but we will actually be closing at the end of October for a major transformation project, and then we will reopen fully in 2028, so do come and see us. And if you'd like to find out any more about the objects or stories that I've mentioned tonight, then there is my book available, A History in Objects. If you just want more of a light touch approach, then there is a smaller book as well called On the Line, which is very much focused on the Meridian story and longitude. So I hope that gives you a flavour of the site, and I'd be delighted to take your questions. Thank you. Yeah.
Thank you very much, Louise, for such a fascinating talk. We have 10 minutes or so for any questions from the audience. And we've got some runners with microphones, so if you have any questions, please raise your hand and we'll get a microphone to you. Yes, one at the front, thank you.
Thank you. I have a question about scientific instruments. I'm imagining at first individual scientists would have to commission a craftsman to help them with that. But how did that sector develop over time? Did you start getting specialist manufacturers developing different sorts of very fine instruments? And when did that happen in the sort of history of science development?
Yes, good question. So thinking about the development of instruments, so at the beginning of the observatory, it was very much the Astronomer Royal working with a master clockmaker, almost on an individual basis. So Thomas Tompion and Flamsteed worked together, and then Tompion would have had maybe a couple of apprentices who would have worked alongside him, and it was quite sort of small scale, based very much on sort of personal recommendation as well. Then later on, by the time you get to, say, the 1770s, you've got people like Jesse Ramsden, the instrument maker. He's starting to develop ways of making instrument making more routine. So, for example, he creates a device called the dividing engine, which means that you can then make scales for instruments like sextants and similar instruments. You can make them quicker and more cheaply and in bigger numbers. But it's still quite a craft level, I guess. London really was the epicenter of the instrument trade in that period, in the 1700s. And then in the 1800s, you start to see more manufacturing, and that's when it really starts to expand more. You have the influence, say, of the Great Exhibition in 1851, where manufacturers are encouraged to showcase their work, and that's when you start to see more companies emerge. But yeah, very much going, I guess, yeah, sort of mirroring other trades as well, going from individuals through to major companies. Are you involved in any particular company yourself? Or?
No, because I can imagine that would inhibit or help accelerate the development. The scientists would have an idea they wanted to develop, but if in terms of materials or operation you can't physically produce really fine instruments, that's an inhibitor potentially, or an accelerator in progress.
Yes, and you can see how different sort of groups work as well. You can see different sort of. Sometimes they diversify as well, so they might start off making telescopes, but they're trained as opticians, so they might be making other instruments as well, microscopes and so on. So there's quite a diversification as well, depending on their interests. Yeah.
Thank you. Are there any... Oh, yeah, the questions at the back.
It was a really good talk, thank you very much. Was the observatory involved in the story of parallax, measuring the distance to the nearest stars? I know the Cape Observatory was, but did Greenwich get involved in that at all?
Good question. I can't think of anything specific off the top of my head, but certainly measurements for the scale of the solar system, definitely. And also they did the opposition of Eros measurements around 1900 and 1930. So this was the close approach of an asteroid that you could then also use as a yardstick for measuring the scale of the solar system. And interestingly, we're coming up to the centenary, obviously in 2030, so we're hoping to promote that story. And also, the Eros one is significant because it was the last time that we really used pure traditional astronomy to measure the scale of the solar system, because after that, we then started using radio signals and also space probes. So it's an important milestone. But good question about parallax. I can't think of anything specific. Do you have any connections with the Cape?
No, but the Astronomer Royal for Scotland, the first one was the guy, the astronomer there. But
Yeah.
this was a German that eventually did it. He had
That's
a very,
right.
very fabulous telescope that took years to build. And I just wondered whether Greenwich might have lacked precision, perhaps, to do what Friedrich Bessel did.
Yeah, that's a good point. I mean, it may be partly because the astronomers at Greenwich felt that it wasn't part of their remit. There was a very strong sense of, we are here for astronomy, for navigation, for timekeeping, asking those big questions about sort of the nature of the universe. That wasn't really seen as something that they should do. And it's quite an interesting shift in that national observatories were very much focused on those sort of practical needs. What time is it? How do we know where we are? Longitude, navigation. Whereas wealthy amateur astronomers were the ones building giant telescopes to look at nebulae and gas clouds and the planets. That was seen as very much what the amateurs did. And it's only later that the two kind of merged in more ways.
Question there.
the items that you cover in your book, are they all on display at the observatory? And do you rotate what's on display as well, and is it constantly change what's?
Good question. Sadly, no. Most of the objects, quite a few that I've mentioned are there. So, for example, the Harrison timekeepers are pretty much on display most of the time. We've had to take one of them off at the moment for restoration, but yeah. Obviously, the telescopes are still very much in situ. But some of the other objects, no, I'm afraid not. We have a collection store a few miles away where we keep most of the collections. And I think that was part of the rationale behind the book, was to sort of put a spotlight on some of these objects that we don't display. And we don't generally rotate the objects that frequently, probably every 10, 15 years. So, yeah.
It's like a shame that you can't really get to see them.
It is difficult, definitely, yeah. People tend to come to the observatory as a one-off visit. They're usually tourists coming to London. They want to see the Prime Meridian. They want to see the Harrisons. So we don't really have scope to change the displays very frequently, which is a shame. But we do have open days at our collection centre where you can book a tour and see some of the objects behind the scenes. So that there are opportunities, but they are limited, I'm afraid. Yeah.
Question down the front.
I don't know if my memory is serving me correct, but I seem to recall quite a few years ago a documentary or something about people who used to deliver time to the City of London.
Oh, yes.
If that's correct, I wonder if you could possibly expand on it a bit more.
Yes, great story, and it does feature in the book. So this is the story of the Belleville family. I don't know if that rings a bell. Yep. No pun intended. So this was a service that was started in 1836 by John Henry Belleville, who was one of the assistants at Greenwich. And he had the genius idea of, why don't I take accurate Greenwich Mean Time to the city, particularly to the chronometer makers, to the clockmakers, because they needed to know the time so they could check their instruments. Traditionally, the clockmakers would have sent the assistant or the apprentice to Greenwich to check the clock and then come back. It's a lot easier if you take Greenwich Mean Time into, well, mainly Clerkenwell, which is where the industry was sort of based. So every week, Henry Belleville would take this little pocket chronometer, checked against the observatory's clocks, take it all around London to about 200 subscribers. He died in 1856, and it was continued by his wife, Maria. So she very diligently carried on. And then when she retired in 1892, it was carried on by their daughter, Ruth Belleville, who became known as the Greenwich Time Lady. And so every Monday morning, she'd come, get the chronometer checked, and then she would work her way across London from east to west, selling the time to about 50 subscribers. Now, by this time, sort of in the early 20th century, you already had time by telegraph signals and then later by radio signals. But people liked still having this very regular, dependable service because, like all technologies, there were failures. There were days when the radio signals didn't work or the telegraph signal didn't arrive. So actually having a human being bringing you the time every Monday morning was very, very reliable and trustworthy. And she continued right up until the Blitz in 1940. But yeah, it's an incredible story. Yeah, there's a book by David Rooney that talks about the whole story if you're interested. Yeah.
I think we had a question here first.
Regarding the choice of Greenwich for the Meridian, could it have been anywhere? I mean, we all love Greenwich, obviously. And secondly, was there any competition? And if so, how was it standardised on Greenwich?
Yes. So in theory, yes, you could choose any meridian because we're on a sphere, so you could choose any one. There is no natural advantage for having Greenwich. It's not defined by the sun like the equator, but it's really very much a human decision. And in particular, you need a very accurate instrument, a transit circle, for measuring that meridian. So that's why it was limited to just Greenwich, Paris, Berlin, or the US Naval Observatory. Those were the four contenders. There was a counter-argument that maybe it should go through the Pacific because then it would be politically neutral because it doesn't go over any land mass. But then where are you going to put the telescope? You need like a little island in the middle of the Pacific. So that doesn't work either. And then because the majority of people were using these British maps and charts, it was just the most pragmatic and the least hassle to choose the meridian that most people were using anyway. So very much a human decision. And it'd be interesting to see how that maps out quite literally on other worlds. So for example, on the moon, there is the prime meridian that is the meridian that faces directly opposite Earth. But there's a prime meridian on Mars that goes through a crater that is actually named the Airy crater after the astronomer Royal George Biddle Airy, who was very much involved with the Airy Transit Circle. So, yeah, interesting question for future generations as well.
One final question here. Thank you.
Right, thank you. Is it true that Newton was against the chronograph approach to longitude and delayed awarding the prize?
I don't know, I haven't seen any specific writings about that. I know that Newton was Newton was part of the Royal Society who oversaw the work of the observatory. Famously, Newton and Halley were getting quite impatient with Flamsteed's reluctance to publish his star catalogue, and that's why they published what became known as the pirate copy in 1712 before the official version came out in 1725. But that's interesting about the timekeeper method. I haven't seen any specific writings about his thoughts on that. So yeah, I'd be curious to know where that came from. All right, okay, yeah. Of course, yes. I don't remember that particular section, but possibly. I mean, certainly clocks were very unreliable at that time, and it would almost have seemed impossible that a clock would give you enough accuracy to work out your longitude. But I don't know the specifics. Thank you.
Great. Well, if we could thank Louise again for such a fascinating talk and answering so many of your questions. I'm sure many of you are keen to get hold of a copy of Louise's book, which you can do so from our independent bookseller, Fox Lane Books, and Louise will also be signing books after this session. So thank you so much for attending today's event, and please have a look at what else is coming up in the festival programme as well. Thank you, Debbie.